everyone, and welcome to this Telit Cinterion webinar, an RF Designer's Guide to Smart Metering Applications. I'm Amanda Flink, the Head of Global Events here at Telit, and I will be moderating today's event. To explain this topic today, I am pleased to be joined by two speakers. First, we have Neil Bosworth, the Head of Vertical Segment IoT Products at Telit Cinterion. Hi, Neil. Thanks for joining us.
Hi, Amanda.
And we also have with us Jordi Miro, the Product Engineering Manager at Ignion. Jordi, thanks again for joining us today.
Hi, Amanda. Thanks for the opportunity. Hello, everyone.
Now, just before I hand it over to Neil to start our presentation, I do have a few quick reminders for our audience. We will have time to answer some questions at the end of our presentation here. You can simply submit a question by posting in the questions box located near the bottom of your screen. Also, please be sure to check out the resources section for some additional information on today's topic. And finally, we will send out this replay link to all attendees at the conclusion of the webinar, so be on the lookout for that. And with that, Neil, I will hand it over to you to start our presentation today.
Thank you very much, Amanda. And it's great to join you here, Jordi. Let's make a start. Because Telit Cinterion's made a significant contribution to smart metering since their introduction for automatic meter reading, say, 15 years ago. There's a key component that makes them smart is reliable connectivity. But as the use cases further evolve, there becomes a greater dependence on reliability as smart meters gather more data than just meter reading today. They become critical infrastructure or automatic metering infrastructure. Naturally, rollouts are large investments with large numbers, so there's a heavy emphasis on cost, efficiency, and reliability in terms of manufacturing, deployment, and the long life cycles that these products endure. But without reliable, efficient, and secure communication, the smart meter is simply not smart. Wireless communication technology has become hugely important and a significant challenge for smart meter manufacturers and deployments. So if we drill down a little into the functionality, we can see smart meters are becoming complex. In fact, they start to look a little bit more like a smartphone, really, but at a fraction of the price and much longer lifetime expectancy. Why are they looking like a smartphone? Well, they're running applications, maybe even third-party applications. They need firmware and security updates, and they also need to solve the challenges of multiple wireless connectivity standards. But unlike smartphones, they're fixed, and they're installed in a variety of sometimes obscure locations, maybe basements, cupboards, closet, in a box outside or somewhere. Here we see a representation of the role of smart meters and some of the common standards they might employ. But you see how they are necessary to manage not just meter readings, but an essential component to balance the grid, really. And it gives rise to a number of challenges. You need to have an ever-evolving scheme for the integration of new smart devices and new smart home devices. You need a strategy to separate the comms from the metering hardware, or the legal part, if you like, from the communications part. And also you need a reliable and long-term and rollout-specific means for backhaul to the head-end system. And this often uses multiple RF technologies. And here I draw a comms hub, but it's not always the case, this separate comms hub. Often the communications, along with the RF complexity, is encased within the main meter, often as a separate comms board with a integral antenna. So when it comes to considering the backhaul to the head-end system, there's clearly a lot of strategies. And here I mentioned just 4 historic techniques. I appreciate there are others, especially in the license-free ISM band spectrums. But these low-power techniques are great, especially in the extremes of population density. But they need to be secure and they need maintenance and additional hardware equipment. And this long life maintenance causes issues for long-term deployments. In-house developed protocols cause issues with interoperability, while standards such as YSUN are addressing low-cost standards-based approach to mesh, which is really optionally suited to certain geographies, especially those that can utilize the full spectrum and have quite a generous link budget. It's direct cellular point-to-point, which is gaining most traction globally, and this is dedicated by IoT-based standards for low cost and low power using 5G new radio. But it's fair to state that cellular technology plays an important role regardless of the chosen topography, and it's cellular communication that's most suited to delivering the roadmap of demands for smart metering. We see trends to introduce more and more cellular connectivity into deployments. Some countries are now delivering their second wave of automatic meter infrastructure as natural product time cycles dictate, and smart meters become more capable to address identified needs and use cases. There's also the possibility for utilities to adopt private networks as they look to address more and more smart energy use cases. New rollouts, especially in emerging Asia, look to learn from successful rollouts elsewhere, say in Europe. And cellular comms sits in a prime position, and systems these days are generally born cellular from the initial concept. There's a vast deployment in India happening right now, and this is a mix. Cellular is deployed depending on the geographical state of India and the technology position of the network operators. And then there's emerging concepts to consider that combine low power radio with cellular, and we'll talk a little bit more about this later. So what is it about cellular that makes it attractive? I mean, clearly it's not free to use, but this roadmap visibility, scale, global standards, and accountability or ownership, along with investments from hundreds of operators, make cellular really a good broad choice for long-term IoT deployments, and especially in smart metering. But it's licensed spectrum with standards, which means there's a globally agreed roadmap as defined by 3GPP, along with all the operational frequencies. And there are multiple branches dedicated to machines, but let's talk about the radio. Millimeter wave is for high-speed 5G, the enhanced mobile broadband branch of 3GPP tree. And that's split into frequency range 1 and frequency range 2. And here we're talking about 6 gigahertz kind of frequencies for frequency range 2. The LTE is generally from low band to high band. And this middle branch, and really it's the sweet spot for many IoT applications, and sometimes electricity meters too. And this is where NR RedCap will fill for 5G with 2 identified releases. The first one being similar in terms of performance to LTE Cat 4, followed by release 18 version, which is more optimized for low power applications. And if we zoom into the LPWAN or MTC branch at the bottom, we see for practical reasons that actually lower bands are preferred, and the MTC branch is where most smart meters live, be it Cat-M for electricity or narrowband IoT, really suited towards water and gas meters. And this LPWAN or MTC, you can use the words interchangeably, technology is only really defined up to the lower mid-band. A previous slide, I talked about easy to deploy and maintain globally. Meter manufacturers don't want to make multiple SKUs. It's expensive, it's tedious. But since the introduction of LTE, cellular bands became somewhat more tedious when compared to previous generations. But let's consider we have a stack with 3 layers. We have the standards, which is the frequency ranges as set out by 3GPP. Then we have the real-world implementation and how they're adopted by the MNOs. And then we have the specialist vertical demands. So looking at the distribution, I mean, don't bother reading the numbers, but there's a lot of complexity. So let's take a reality check, which means different MNOs and the actual implementations. So depending on the frequency options and the frequency baseline is defined, and depending on the metering service provider or utility organization, you might have some specific band preferences in the public bands. Then there are bands that have been specifically, let's say, pushed by utility organizations. And if we look towards the extremes, we see that there's been an extension of LPWAN towards 400 megahertz or 450 megahertz. And really, this is being driven by the metering natives. Telit Cinterion is an active member of the 450 Alliance, and this 450 spectrum is convenient for utilities to deploy their own private network. And I've just highlighted on this map regions with deployed networks in this spectrum. It's not exhaustive. There's other proof of concepts and trials, generally for utility use cases and public safety use cases too. Why would you use 450? Well, it's simple, really. You get the longer range, which means less infrastructure, as in cell towers, and better penetrations into buildings. But the lower frequency presents a challenge, the bigger ground plane and a challenging antenna. It could also be the case that a standard public network and a 450 network is required on the same device. Private networks is a trend that can be attractive to utilities, and I also mention here Antarix, who target utilities with their 900 megahertz spectrum in the USA, but others do exist, and these private operators have their own approvals or requirements which Telit Cinterion addresses with modules to suit. MTU technology, the frequency band, at least sub 1 gigahertz. And in Europe, for example, band 20 is the most common. In the US, 12 or 13 maybe. So due to the lower complexity of MTCs, all the modules support all the bands globally, and rarely is there a need to make a specific variant for public networks for band coverage reasons anyhow. So I mentioned this stack. We address this stack by being an active member of the 3GPP with excellent relationships to MNOs. And on top of that, we have dedicated vertical teams to address this last layer. Many tenders now include the use of eSIM, and this demand is driven by its flexibility. With the three requisites of smart meters, i.e. a lot of devices, remote devices, and with long life cycles, three use cases tend to emerge. The first one being manufacturing, and really this is the idea of subscription management here is to provision different MNO profiles during the production of the meter. And then you have the install use case where the meter might choose its most suitable MNO profile, maybe with the best signal strength during the installation to make life easier for the installer. And then you've got this maintain column, which really allows the meter to switch mobile network operator during the long lifetime of the meter. And this could be, of course, to onboard private networks as they get rolled out. But when you switch MNO, you could be in a different frequency environment, and this can do two things. You have a direct effect that you can measure due to different attenuation, and then you have a logical effect. So a change in frequency, yes, it can impact the reception, but it can also impact the power, and impact the power in a couple of ways. One by this attenuation absorption effect, and the other one could be power, which could be an exponential growth by triggering different system behavior. For example, repetitions, which not only have power implications, but they could have airtime cost implications as well. So you have a direct effect that you can measure due to different attenuation, but then a logical one which links to the system. How's the system going to behave with respect to repetitions? Well, that's something that perhaps you didn't design for at the start. So in conclusion to that, it's important to work with us from the start of the project to kind of think through these different scenarios. We've got a lot of modules, And if you open up a smart meter, you'll probably find that these are the devices, these devices here that I highlight are the modules that you're going to find globally in smart meters. As can be seen in the chart, we're supporting multiple devices in the MTC branch of 3GPP. You see footprints offering migration across the families or technologies to facilitate the most possible flexibility in design. The LTE-M devices and the narrowband devices, due to the nature of these technologies, as I mentioned a few minutes ago, they tend to support all the frequency bands for global deployments. On the left there, you have a couple of narrowband parts. One has a variant, one's a variant with 2G fallback. The other one supports this connectivity activation eSIM subscription management initiative that we have. Moving across to the right slightly, you see CAT-M has lots of variants, and I won't take time going through each one, but you'll find CAT-M only devices or CAT-M devices that support narrowband IoT. And some of these devices support LTE 450, which does need a dedicated 26 dBm transmission power, whilst normally the standard is 23 dBm. Sometimes fallback to 2G is required, so we have variants where you need this support, although truth be told, it's becoming less and less as time goes on. And then the row above, the middle row, with Cat1, there are multiple devices with footprint compatibility, and these tend to follow either global or regional SKUs, which you don't need in the MTC devices. And then we have Cat1 BIS, which is a simplified Cat1 device. And probably the key difference here is only one antenna supported, so there's no RX diversity required. And finally, for me at least, a view of the future. In some countries, especially those with legacy ISM mesh deployments, hybrid approaches are being investigated by combining the benefits of cellular with the potential license-free and low-cost approach of ISM-based technologies. We're looking to embrace this concept by supporting both cellular and short range. Both of these communications protocols, or both of these styles of communications protocols, within the same device. And we're looking at protocols that are primarily targeted towards those chosen by smart meter manufacturers. Clearly, it's a nice idea for meters, adding infinite scale and flexibility to address the future demands of smart meter deployments. Now, using our GSMA standard method of over-the-air network provisioning, we can make the most adaptable IoT cellular networks. And with short range, we can support standards such as WISUN, and a view to even further in the future for the most remote devices, well, they could potentially be reached by the use of non-terrestrial networks in 3GPP release 17, and that can be addressed directly using narrowband IoT. But back down to earth again. With that very brief introduction to cellular connectivity and smart meters, I'll hand over to Jordi from Ignion to detail some strategies to address the challenges of antenna design in smart metering. Jordi, over to you.
Thank you, Neil, for your words. And hi, everyone. Let me introduce myself. This is Jordi Miró, the Product Engineering Manager at Ignion, which mission is to simplify the IoT design journey by integrating the antenna in the easiest way. In this presentation, we will see the main challenges you may already know and face in the smart metering world and how Ignion can help you to solve them. So we already know that it is challenging to deploy a successful smart metering solution due to multiple problems associated with the antenna. We know that making robust and reliable connectivity is really hard, and we make it easy with our cloud-based design tool. removing the risk of weeks of expensive iterations on manufactured physical prototypes. These physical prototypes typically cover multiple bands, so you will be glad to know that the virtual antenna technology that Ignion owns is easily customizable for any spectrum for 400 megas, covering this new LTE 450 band to around 10 gigas, and can cover multiple wireless standards with the same single pair number. Once the antenna system is tuned to the desired frequency range, it's very important to consider also the different materials that will be near the antenna in the surrounding area. We will see how important it is to anticipate the effect of materials in proximity when the smart meter is deployed. That deployment that will last for many years thanks to a high antenna performance solution that Ignion can deliver, taking care of the batteries and chipsets and ensuring the low power consumption of the smart meter. Related to the challenges, let me show you how the Ignion solutions for all of them. Ignion offers a simplified and complete solution that is the combination of the virtual antenna technology, shown at the left of the slide, and the Antenna Intelligence Cloud design tool, with customized support for designers at the right of the slide. Firstly, the virtual antenna technology consists of three main elements. As you can see in the image of the left, the antenna component is the red part number from a family of 6 products so far, able to cover any wireless technology such as the LTE, Narrowband IoT, Wi-Fi, and so many more. The matching circuit consists of a series of lamped components that match the antenna response to any frequency range, basically consisting in inductors, resistors, and capacitors. And finally, the ground plane, which makes the whole system radiate properly to the matched frequency range. The bigger the ground plane, the better will be the antenna performance. This statement is very important for the next slides. This antenna system can be easily configured from the first stage of the design process, thanks to our Antenna Intelligence Cloud design tool that put your design on the right path from the very beginning. By filling out a 1-minute form, you will get a complete report with topologies, bill of materials, design recommendations for your smart meter, and antenna performance of your design, being S11, reflection coefficient, and antenna efficiency. I invite you to check this tool by going to our website, ignion.io, and clicking in the top right corner that says Free Antenna Design Tool. And don't worry, this is a free of charge tool. Moving forward to the design stage, here is listed the list of challenges that we will review in the following slides as the main challenges in terms of antenna integration for smart metering, which consists basically in these bullet points. For example, multi-board connection, that we faced several times, this typical connection with the main PCB, having the screens or other elements for the smart meter itself, and a separated board for the communications, having there the antenna, the matching circuit, the ref module, and the chipsets related to communications. We will see the challenges for combinations of wireless technologies, such as this LTE plus the new LTE 450, but we can see others such as short-range sub-giga frequencies, such as ISM 868 band, or the 915, 2.4, 2.5 Wi-Fi, and many more. We will see also the materials in proximity, as I said, and how we can assess the impact for your deployed smart meter. We know that the certifications for smart metering is always a must at the end of the design and can cause several redesigns on the design, and the challenges regarding the battery life and how we can solve them. One of the typical configurations inside a smart meter is this multi-board configuration, having a separate board for communication, as I said before, with the antenna. In this case, it's a simulated environment where for the left image, we can see the communication board connected to the short edge of the main board as a hat configuration. And in the middle, we see how both boards are connected through a 14 array of pins. with two of them connected to the ground, ensuring the grounding between the main board and the communication board. But you might be thinking, this pin connection is random or it is calculated. Well, properly connecting this main board with the communication board makes an impact on the antenna performance. We can see in the right graphs how, depending on the connection point, we get better or worse performance. The fact of locating the connection point in one position or another is decided through the simulation image at the left of the slide, based on the propagation of electrical surface currents that can be assessed through electromagnetic simulation service that Ignion offers. The main idea is to find a location for the pins where the electrical surface currents are strong enough to be propagated also through the main board, enlarging electrically the ground plane as much as possible, maximizing the antenna performance. As you may remember, in the previous slide, I said the bigger the ground plane, the better the performance. So taking advantage of this pin connection, make sure that the antenna performance is optimized for your smart meter. This is a pin connection solution specifically for the simulated environment, and we have been working on. Ignion can help you with your specific case, starting with the design recommendations gated in the Antenna Intelligence Cloud report that you might get if you fill the form accessing to by the website. Also, it's very important to consider the interference caused by that pin connection. Using RF choke inductors, reduce the interference and optimize antenna performance, leading to enhanced overall efficiency. Of course, all of these recommendations can be recommended through our services and inside the Antenna Intelligence Cloud report. Now that the multi-board setup is properly configured, we can talk about multiple wireless technologies within the same communication board. This is one of the examples that Ignion delivers, between many more, combining the new LTE 450 band and the low-power cellular technologies, such as this LTE-M frequency range from 700 megas up to 2.2 gigas, will be a globally coverage. And both antennas, both wireless technologies, are in the same in-pin-out port thanks to a two-stage switch, selecting the cellular antenna for this 700 up to 2.2 gigas, or the LTE 450 antenna, that will be the antenna on the right. Other combinations can be evaluated, such as adding these short-range sub-giga technologies and many more, either using one or multiple antennas. The tailored capabilities of the virtual antenna provides limitless possibilities. But of course, all the challenges are not only inside the device, within the design. It is very important to consider the surrounding area where the smart meter will be deployed. In these graphs at the right of the slide, you can see the performance for three different materials, starting from the left. We have wood, concrete, and metal, compared with the free space measurement versus the distance. As can be seen in the bottom graph, the performance is more robust at a certain distance compared with the graph at the top, when the board touches the material and the performance gets dropped, especially for metallic materials. As a best practices we typically provide, we recommend always keep certain distance between the antenna and metallic elements, and consider materials in the antenna performance test. In case the material system does not respond, this can be always fine-tuned to the matching network, optimizing the deployment of your meter depending on the surrounding area. For the performance certification that all the smart meter manufacturers must surpass, and before going into the manufacturing stage, these are the best practices we recommend to follow to surpass any certification target. First one, at the very beginning of the design stage, is focus on the deployment bands of your meter. bands that can be easily tuned through the matching network thanks to the capabilities of the technology, and follow the design recommendations gathered initially in the Antenna Intelligence Cloud report and then from the technical team that will guide you through the certification stage. The use of the high Q factor and low loss components will enhance your overall antenna performance. And before going into a certification that takes a lot of cost, Ignion can guide you and evaluate the performance of your final device, providing you with TRP and TIS results for the bands to be certificated. The table in the bottom corner shows an example of assessed performance based on simulated results, and injected power values are as per the TX62 Telit module that provides 26 dBm at LTE 450 bands and 23 dBm for the this example for the North America bands 2, 4, and 12. All of these results are from the simulated results we've seen in the previous slide, and is calculated through TRP through the antenna efficiency. Okay. Of course, environment and power settings matter, and following all the steps mentioned before, such as you can see in the image of the left in the slide, you see the proper pin connection. By fine-tuning the matching network for your final smart meter, for your final prototype, we will see that the power injected through the by the module is totally directed to radiated power, having an optimized antenna impedance, which means a good battery life and ensuring the reliable communications and the robustness. On the contrary, if we don't follow all of these recommendations, for example, the pin connection is not optimal, the matching network also is not matched to the desired frequency range, all the power injected by the module gets directly reflected through the chipset, and then means that the chipset will have a lot of damage and making this smart meter in not working status, or reducing battery lives in one of the worst scenarios and having a poor quality of the communication. All of these steps are within the simplified virtual antenna design journey that guides you from the very beginning stage of your smart meters, starting from the Antenna Intelligence Cloud report that can be tested in our website, in ignion.io on the top right corner of the window, and up to certification stage, passing through the design stage in the Gerber or CAD revision that are free of charge inside our services, electromagnetic simulations of your full device, an optimized matching network for your manufactured smart meter, and at the end of the design stage, over-the-air measurements per certification stage that will ensure that you will pass all the certifications to the first try. Further explanations gathered in the link shown in the bottom of the slide. To check again all the results shown in this presentation and to see further information, you can download our new design guide for smart metering, which will include more information about successful smart metering design with much more detail on what we have been going through today. For example, more PCB size analysis, more best practices for certification stage, and many more. Use this QR code, scan it to get started with your next project. Thank you for listening, and I think it's your turn, Amanda.
Yes, great. Thank you so much. And again, you can check out the resources section here as well for that smart metering guide. Now, before we get to the questions, audience, I am going to drop a poll on your screen. If you'd like to have somebody contact you directly, please just respond here on the poll, and we'll be sure to have someone reach out to you. We do have time for a few questions, so we will do our best to cover it in the short time that we've got left here. And Jordi, it looks like this first question is for you. It says, out of the challenges that you described, which would you say is the hardest?
Well, I think from the technical perspective, and totally in my opinion, I think the worst, the most difficult challenge, sorry, is the pin connection between the main board and the communication board, because you can do everything okay, but if you miss in this connection, the performance of the antenna can be dropped drastically, as we've seen in the previous slide. So I would say the pin connection that can be assessed and can be properly configured through electromagnetic simulations or by proof and error. This is also a valid proper way to do.
Great, thank you. It looks like this next one is for you as well. Given the overall complexity of the product, can Ignion predict fairly good performance?
Yes, this is within the design journey that the Ignion follows with all the projects. Starting from the Antenna Intelligence Cloud tool, that this is one of the services that is more in the side of the customer, that can calculate and can assess the performance of their very beginning design of their device, assessing performance and having design recommendations, topologies, and bill of materials. But then there are, we assess the performance on every stage of the design journey, starting from the curve review, starting from electromagnetic simulations, and then with the matching network service with the final prototype, and in the pre-certification stage. So yes, in every step of the design, we can predict fairly good the performance of the device.
Great, thank you. Neil, looks like this one is for you. The device you showed that has cellular and short-range capabilities, when can we expect to see that?
Okay, so we're quite excited about the ME310 M1. It gives us lots of scope for creativity, and it allows us to try all sorts of different things. You can probably expect to start to see samples towards the end of this year, early next year. But of course, because we can do so much with it, you can expect to have a series of devices supporting different things. And right now, we're in, the product's defined, but we're in the stage where we're also collecting use cases. So whoever asked that question, please do feel free to contact us, because I'd love to discuss your use case so that we can get the product exactly right, supporting the right protocols in the right way. So please do reach out and let's have a chat. Thank you.
Thanks, Neil. I think we'll take just one more question here. This one says, is coupling being taken into account between antennas in your simulation? Jordy, this one's probably for you.
Yes. Well, in the slides we saw this combined LTE 450 and the cellular IoT antenna. And to be honest, these both frequency ranges are quite separated each other, so there is no coupling there. That's why it's not shown in the slides. Sorry about that. But every time we assess the performance of any device, of any solution from our customers, we always show the coupling, and we take care of that, reducing as much as possible this undesirable effect.
Great. I believe that is all the time that we have for today. Audience, please be sure to check your inboxes in the coming days for that replay link if there was anything you missed or want to review again. Neil, Jordy, thank you so much for your time today, and thank you everybody who joined us. Have a good one.
Thank you.
Thank you, Amanda. Thank you, Neil. Thank you, everyone.